will give you an example of this. Okay, for example, suppose somebody is growing some corn, and then you think that the corn yield is affected by several factors. Fertilizer. Okay, so let me just create it. Okay, so you have the corn yield. Okay, the corn yield there, and you believe that this corn yield, okay, is affected by some factors, affected by fertilizers. Okay, let me call it fertilizer. But is also affected by other factors. So let's call it UI. Those other factors, we don't know them, we don't see them. In fact, we can't observe them. We don't know when. And even if we can observe them, we don't control them. You see, the fertilizer, you control it, but the rainfall, you don't control it. You don't control the rainfall. So the rainfall becomes a latent, a hidden, unobserved factor. You can't control. Those factors are uncontrollables. And they are critical. Because what if there are many of them that are truly affecting this corn yield and you didn't capture them? So you got to deal with them. And in the process of dealing with them, that is when you handle the true factors. So let's go and look at assumptions of regression, because the power of assumptions of regression is this. The assumptions of regressions are as follows. Sometimes we call them the properties of the OLS estimators. You will later very soon learn about this word OLS, ordinary least squares, because that is the approach we are going to use to find that beta parameter and move it to the numerical coefficient. What are assumptions? Well, assumptions are certain things that got to be in place for certain things to work. Now, the moment you say that the moment you make something like the university is working, classes are ongoing. The moment you make that statement, classes are ongoing, you have already assumed that there is what? Or there are what? There are lectures. There is a university building. There are libraries. There are computers. Okay, there are students. Because you can't say that the university has started working when there are no students, there are no lecturers. So assumptions, in simple language I'm giving you, assumptions are certain things that have to be in place for certain things to work. And number one assumption in regression, in the estimation of the numbers and moving the numbers from the beta parameters to the numbers, one of the assumptions is that the error term, its expectation. So this word, the expectation of the error term given the independent variables should be 0. What does it mean? It means that we are expecting that error, those factors that we said are hidden, we are expecting that they are 0. We are expecting that eventually they will not even be there. Now, why should we expect that? We got to expect that because if they are there, we will not be able to better explain how those independent variables are affecting the dependent variable. So one of the assumptions of regression, and this is critical assumption, is that there must be 0 mean value of the error term. The error term must have a 0 mean. You see, I did not say the error term must have a 0 value, no, but mean, which means that there are a number of the error terms. There are a number of them. And because there are a number of these error terms, when you average them out throughout, you must have what? A 0 mean. Let me do a quick drawing to explain how this thing is. Remember these values, these stars that we drew? Okay, fantastic. Now I want us to draw a line. Let's say I want to find the mean. You see, if I told you here, if I want to find the mean between this, I can draw some lines in here. Okay, I can draw some lines in here. Okay, because it's clear. Now, but with this, there are so many numbers. So I can now look at the gap there in between all of them. I can throw a line, a mean. I can find a mean. I can find a mean, and I can draw that mean like that. I can draw that mean. That line is called a fitted line. It's a mean line. It's an average line. Suppose you have somebody who is 30, 40, 60, 70, 80. Okay, you'll find the mean. That number, but this time it's not a number, but they are scattered. They are scattered. So you try and get one line where on average, everybody is closer to the line depending on where he is. But I want you to look at this line here. You see, if you look at the line here, the guys on top here, okay, they are far away from the lines. But there are some guys who are closer to the line, closer to the line, closer to the line, far away from the line, far away from the line, closer to the line, far away, and all of that. Now, those gaps there, between where that observation is and the line, those are the errors. Those are the errors. Those are the errors. Those are the errors. So every observation, how far it is from the line is its error. So there are errors. Those that are above the line, the errors become positive errors. Positive because they are above. Those that are below the line, like these ones, the errors become what? Negative errors. So they are below. But the line you have drawn is a mean. So the assumption we are looking at, the zero mean assumption, says if you are to add up all of these errors, if you are to add up the errors, add them up, because some of them are positive, some of them are negative, some of them are positive, some of them are negative, eventually the mean of those numbers, the gap, remember when you want to find the gap, you just read the number here. Suppose this one is 6, and then the one here, suppose that one is 2, then it means that the gap for that one will be positive 4. So you now add positive 4, add this positive 2, add this negative 1, and then once you add all of them, some of the positive will cancel some of the negatives and all of that. Eventually, the mean of that gap should be what? Should be 0. This is one of the assumptions of regression. So because if they are 0, then it means there are no errors. And I'll prove this mathematically for you. We'll solve it in R for you to see how beautiful this thing is. So one of the assumptions is that the error term must be equal. The expected value of the error term should be 0. This assumption is called weak exogeneity. You will come to accept it later time, not now. Okay. There is a strict assumption called the strict exogeneity. Now, the reason is because, you see, when I said the expected value of the error term must be, relative, given the independent variable should be 0, I was talking about only one independent variable. I was talking about independent variable that is just for this year. I was not talking about independent variable that changes across time. You remember I said we are doing cross-section. So because it's cross-section, we are all in this year. But when you move from this year to the next year, there is not just one independent variable that is here, but that same independent variable, xi, it is appearing in another year. So it will be xit1, xit2, xi3. So that same independent variable is appearing in other years. And so it means that the errors become what? Plenty, more or less. So in a panel data, there are more of the years. And because there are more of the years, then when you're making the assumption of the zero mean, it got to be strict. So that I no longer becomes I, but it becomes xt, where the t is equal to s for every other year. So this one is indicating that the expected value of a particular error term across time, given, this line means given the independent variables across different observations and different times, okay, should be 0. So in simple terms, the error term should also be 0, but we are not forgetting the fact that it can be across different time period. This symbol means for every s, for every time period, for every s, or for every time period. One assumption, just one assumption of regression, and you can see how we have dissected it in total. So remember, one of the things I said is assumptions are certain things that have to be in place for certain things to work, isn't it? Okay, so this thing got to be in place. So don't forget this thing, because as we go on, we'll prove that, and you see how beautiful it is. Okay, and you might forget that we assume that this is supposed to happen. So don't forget that we have assumed that the mean of the errors should be 0. Second assumption, homoscedasticity. Depending on where you were born, okay, you can say homoscedasticity or homoscedasticity. It's a very long word. Homoscedastic. Okay. That is talking about variance. Now, spread is scedastic. Scedastic means it's a Greek word for spread. Okay, how spread. Now, the homoscedasticity assumption says that the variance of the error term must be constant. Now, this is mathematical way of writing it. var bracket ui given the independent variables must be constant. Now, that symbol, look at it very well. This symbol, if you can remember, is a variance symbol. This is a variance symbol. And the square root of this is usually what? The standard deviation. Do you remember the good old days? The standard deviation is a square root of the variance. So this is the variance. And this variance has nothing multiplying it, so it's constant. What is that? What does it mean? Well, in short, you remember we said that the error term is indicating the gap between where you are and where you are going. Remember? That gap there are indicating the errors. So there's a gap. There's a gap between this and the line. There's a gap. These are all errors. The next assumption is that the way the data is structured, the variance here is talking about the spread, whether it is nucleated together or scattered. If it is scattered, it got to be scattered all through. In that case, the variability is the same. Okay, I'll give you an example of something where the variability is not the same. Okay, that will help you to appreciate it. Suppose I give you something like x here, and I give you something like y there, and then you have something like this spread. Watch the spread. Okay, watch the way I'm doing the spread. Watch the way I'm doing the spread. Okay. Watch the way I'm doing the spread. 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 Now, if you look at this data, watch the edges. It starts somewhere here, it passes the edges there, and then eventually it goes that way. Okay, I'm taking the edges. If you take this one to passes here, and eventually. Now, if you look at the spread, now if you were to compare that one to this, okay, watch this one. Okay, watch this one. Okay, watch this one. Okay, watch this one. Now you can see a bit of a difference. Okay, if you look at this, if I take the edges there, okay, I've missed it because of my drawing capacity. Okay, if you take it here, and then this one would normally go that way. You can see that in this first case, the variability is not constant. Do you realize that? This is not constant. This one is not constant. When I say it's not constant, I'm sure you understand it. It's not constant. The gaps between them are widening. Okay? So you can see that there is a bigger variability as you go further. As you move from left to right, you can see that the variation, the spread, the dispersion is widening. And that means that there is no constant spread. There is no constant variation. But if you look at this one, okay, it appears that they are all kind of, as you go further, the variability is the same, more or less. Do you realize that? The variability in the second one. So here, there is constant spread. Yeah, there's a spread. There's no doubt about it. There's a spread. But the spread is what? Constant. When the spread is constant, when the errors, so if we plot the errors that I showed you earlier, okay, let me now go back to the, when we plot the errors have to be constant, you know, across the residuals. The errors, by the way, are also called the residuals. So the residuals have to be what? Constant. Some of these terminologies, gotta just write them down. The residuals have to be constant. You see, now I'm using another term for it. Instead of using the UI, I'm now using epsilon. I told you that I'll be using that. So you can say that, in short, these two assumptions I've said so far, they are being represented by this. So the error term is independently and identically distributed. That's how we call it. Okay, find out about this on your own. It's independently and identically distributed. Okay, and we say it's normally distributed with a zero mean coming from the top one, the first bullet, and a constant variance. The I here is simply indicating an identity matrix that shows that there is a constant variance. Of course, this one here tells you this is a variance. Sigma square is the variance. The square root of that sigma square is the standard deviation. Okay. So in a matrix form, you just add an identity matrix. So what this is forget about this. What this is saying is that the variance of the error term should be homoscedastic. Homo, constant, scedastic, variance. Okay. So constant variance. So the variability has to be constant. This is the second property of the ordinary least squares estimators. Wow. Let's go to the third one. So keep this, okay? The variance is important. The next one is that there should be no serial correlation of the errors. Now, do you remember I told you that every observation has got its error? Some of them, the errors are positive. Some of them, the errors are negative. Okay. Now, there should be no correlation. Do you remember we've done correlation? A correlation is when the relationship between two variables are highly close. Suppose a husband steals from the workplace and the wife is called, because the husband says on the day of the stealing he was with the wife the whole day. The wife is called in the courtroom. The wife was asked, Mrs. Smith, your husband says that he was with you on the 31st night of December the whole day. True or false? Now, if that woman is a very Jezebelic woman, very, very strange looking woman, and she wants to finish the entire resources and the wealth of their husband, she will look at the judge's face and say, which man? I don't know this man from Adam. And trust me, the man is gone. The man is gone. But I'm just hoping that that woman is not one of those women among us here. Okay? Because our women who are on this platform are all honest, faithful, and trustworthy. Is that not the case? Is that not the case? Yeah. I can imagine one woman is sitting down there and is saying to herself, you don't know how wicked I am. You just don't know how wicked I am. If you knew, you wouldn't even say that we are all fantastic. Okay. But let's assume that the woman is one of the fantastic ladies that we know. And then that lady, you ask her, Mrs. Smith, your husband says he was with you the whole day. Now, the woman will get up and say, of course she was with me. Now, even if the husband wasn't with her, she is saying that he was with me the whole day. We were having a rollicking time of ourselves. Now, why do you think the jury will not be surprised about that answer? Why do you think the jury will not be surprised about that answer after all? Well, they will not be surprised because after all, the two of them are highly correlated. They are close. They are husband and wife. And so, that is it. Okay, so that is why in most law cases you don't bring the wife to come and testify, because the possibility of the thing going to the extreme is high. Okay, now exogeneity has to do with the gap between how something is related to something. It is not necessarily the independent variables. So don't mix the two. Okay, we can talk about exogenous variables, but then the gap between two variables can be the gap between two things. I want to use that to address the serial correlation, the story I just said. Now, when the errors depend on each other, in this context I gave you, you can see that the husband is dependent on the woman, and the woman is dependent on the man. They are so close. You see, when two people are close like that, it's quite difficult to disentangle them. It's quite difficult to separate them. Like you sometimes know a husband and a wife who are always fighting. If you don't take care and you try to side with one, you are doomed. Because once they come together, because they're already close, they will blast you, they will insult you, they will say that you are the worst enemy. And the reason is because they are so close. When they are so close to each other, it means they are dependent on each other. When they are dependent on each other, we say they are highly serially correlated. Okay, but when they don't depend on each other, when they are not, in tune with each other, we say they are orthogonal. So when two things are not closer to each other, we say they are orthogonal. When they are two things they don't depend on each other. The husband that doesn't depend on the woman that doesn't depend on the man, they are just way far apart like enemies. We say they are orthogonal. So one day you can speak to your husband and say, why are you so orthogonal with me? The husband is likely to ask, what kind of econometric question is that? Okay. But the key point is this: the error terms have to be orthogonal. They have to be independent of each other. The error term with one particular observation should not have any correlation or covariance with another error term. And this is known as no serial correlation. No serial correlation. So no serial correlation has to do with the errors. You see the way I've written it. The covariance between error UI and error uj should be equal to 0. The covariance between error ui and error uj should be 0. In other words, there must be no correlation between the errors. That's why it's supposed to be 0. Where the I is not the same as the j. Because if I is the same as the j, then they are correlated already. Okay. So this is one thing that mustn't happen. The errors. You can see that the first 3 assumptions are all about the errors. The errors are important in regression. Let's go to the next one. Okay. The next one has to do with the zero covariance. This time between the errors and the independent variable. Please note, this is what sometimes is called endogeneity. But we'll come deeply into that. This is what sometimes is known as endogeneity. You put it down. You see, it's not everything you're going to understand here, but you got to put the words down. Later on in the future, you will understand. Okay. Zero covariance between the errors and the independent variable. You see, each independent variable is observed, and each error is not observed. So why are they related? So imagine, let me give you a typical example. Imagine that experience is saying that I can increase the wage big time. But what experience doesn't know is that there is an invisible, unobserved factor that is influencing that experience before that experience is affecting the wage. I'll give you an example. A typical example is what we know in the agricultural sector. Supposing that you get a big bumper, great yield, okay? In the agricultural sector, okay, you get a big bumper. And in this big bumper, okay, there is a lot of boom, you know, cassava, rice, you got a big bumper. And you believe that this increase in the rice yield or the corn yield is because of the fertilizer that you gave. Because that particular year, you fertilize the land so well. And so now that there is a big bumper, you believe that it was because there was an increase in fertilizer. That is what has led to the increase in the rice. Now, while that may be true, what you didn't see, what you didn't observe, which was an unobserved term, was that without you knowing, there was also rainfall, which you didn't control. Okay? There was rainfall. And that rainfall led to you getting the bumper than the fertilizer. Or maybe something else. Maybe you might say the rainfall, you can see it. Okay? But maybe something else you don't see. Or let's assume that somebody is now sick. Okay? Now, I love this as a typical example. Coronavirus. Let's say that your mother, okay, not your mother. Let's say somebody's mother. somebody doesn't want his mother to die, so I don't want to use that. Okay, so let's say that your father or your family member, okay, your friend, somebody, okay, the person is sick. Unfortunately, the person dies. Okay, the person is sick, and unfortunately, the person dies. And then the doctors did some postmortem, and they were able to realize that the person died because of diabetes. Because all along, this guy has been having diabetes. And the person dies. So we ascribed everything to diabetes. But without any doctor noticing, no COVID-19 test was done. And without them knowing, the person died of COVID-19. And so that person has died. There has been an influential factor, an unobservable factor that behind the scene has influenced the person. Not that it's only the COVID-19 that killed the person, but it has influenced the person's diabetes for the diabetes to now kill the person. there is some correlation, covariation between the COVID-19 and the diabetes. They have correlated with each other and has caused the death. So sometimes a person will have hypertension, okay? And I'm bringing my medical knowledge into this. Sometimes a person will have hypertension, and I know for sure that the person has diabetes. But the person will tell me that, doc, I don't have diabetes. Then we go and do diabetes test, and then we realize that the person have had diabetes for 4 years. He's not even aware. How come? Because there is a latent, hidden, unobserved factor. And so when there's that kind of correlation, you cannot ascribe the death to only that one factor. And this kind of hidden is dangerous than the ones that are not hidden. Because when there's a covariation, this is important. When there's a covariation between the error term and the independent variable, okay, when they are not independent, and we are expecting them to be zero, independent. Sorry, there must be zero dependency. So there must be independent. So there must be zero covariance between this error term and the independent variable. Finished. The correlation should not be there. They must not be related in any way. They must be unrelated. The next assumption. Oh dear me, assumptions of regression. They are powerful. Okay. The next assumption is that the regression must be linear in parameters. Let me tell you what I mean. This is very simple. Linearity assumption. Now watch this. You have y equals to beta naught plus beta 1 x1 plus beta 2 x2, okay, plus the error term. Okay, so this is a simple, kind of a two variable case of regression, okay, plus the error term. Now, the parameters are the betas. We know this already. We said that the regression, this is an equation of a line. The relationship between y and beta should be a line, a linear relationship. There must be, so there must be no quadratic relation. In other words, there mustn't be any beta 1 that is squared. In fact, you can have the x's squared. So you can have y equal to beta naught plus beta 1 x1 squared plus beta 2 square root of x2, okay, plus the error term. You can have this. So they must be linear in parameters, but they can be non-linear in the regressors. They can be non-linear in the independent variables. So the relationship between the y and the x's can be non-linear, but they must not be linear in the parameters. So the beta 1, the beta 2, they must be purely linear. No square root, no logarithm with it, no log linearization, no cube root, no cube, no nothing. No, you can even multiply 1x. You can have y equals to beta naught plus beta 1 x3, beta 1 x1 x3 plus beta 2 x2 squared x3 cube. You can have all of this. You can have all of these situations. You can even log some of the x's, but you can't touch the betas. This is a simple. The relationship must be purely linear in parameters. Okay, so it can be non-linear in the regressors, but not in the parameters. Okay, so we are saying that the model can have logarithms. The model can have logs. Okay, do you remember the quantity demanded of gym betas that we had? Do you remember we did something like quantity demanded of gym betas the last time? You remember? Or it wasn't you guys, I thought you that, right? Okay. That data set with the quantity demand, the Burkutu Ventures. Wasn't it this class? Was it this class? Okay. Let me see. Okay, perfect. So it's in the video. Somebody has confirmed that. Now that variable, you can take the log of the kill. Okay. You can have the log of the kill. You can square the variables. One thing you can square is something that you believe that it rises and falls. For example, our incomes can rise, get to a point and fall. For example, when we get to pension, our incomes can fall. A person's occupation can rise and fall. And then you can also interact some variables. For example, you can interact your income and your occupation. because they move together occasionally. For example, okay, your income, as your income is going up, as you are increasing your occupation, okay, a person can be a doctor and an engineer at the same time, and that can lead to the person's income going up. Okay. And also, a person's income can go up because of the location of where he is. So you can interact them. Interacting them means multiplying them together. All of these variables, you can do something about them, but you can't touch the parameters. That's all we are saying for linearity. The assumptions of linearity can be tested. It can be tested. I'm taking my time to walk you through the Gauss Markov axioms. That's another name for the assumptions. Okay? It was indicated and published by this guy called Gauss and Markov. Okay? Sometimes they are called the classical linear regression model assumption. The classical linear regression model assumption. Okay, so that is assumption number 5. Have you observed that? 4 of them are all about the error term. And now we have one which is about the parameters. Let's go to the last one. Oh, not the last one, last but one. The last but one is known as no perfect multicollinearity. Or better still, no high multicollinearity. To be honest, this is something we've already done, and it is something that is easy to understand. The independent variables, the x's, they must not relate to each other. If you can remember, there was an assumption of zero covariance here. That we said the errors and the independent variable must not relate to each other. The errors and the independent variable, they mustn't relate. Okay, but this time we are rather talking about 2 independent variables, xi and xj. They must not relate. Xi and xj. What is multicollinearity? Take your pen and paper, you can write this. Multicollinearity occurs when 2 independent variables, independent, not dependent, 2 of the x's, okay? When 2 independent variables, so I can go back here and I can take any of these 2 independent variables. Let's take an independent variable like education and experience. When 2 independent variables are so highly correlated that it is difficult to separate them. It is difficult to disentangle the partial effect of one from the other on the dependent variable. That is PhD. Let me just explain it again. Multicollinearity occurs when 2 independent variables, okay, they are all trying to explain the dependent variable. 2 independent variables are so highly correlated. So when you go and check their correlation coefficient is so high. The independent variables are so highly correlated that it becomes difficult to separate the partial effect. When we say the partial effect, they are individual singular effects that each one of them is having on the dependent variable. It's difficult to separate it from the other. I'll give you another example. It will help you to best understand it. And I'm going to take this education and experience. Watch me. Watch me. Watch me. Your salary is affected by your education. And then your salary is also affected by your experience. We all know this. But let's assume that in your company, you realize that so many people are going to go and do their PhD. You've observed this thing for the past 3 years. There are a lot of people go and do their PhD. When they return, their salaries are doubled. And you start getting angry. You became so angry. One day your boss sees you and he says, "Johnny, why are you so angry?" And he said, "Why wouldn't I be angry? Because I have been here 3 years and I've been seeing people going up and down to go and do their PhD. They come back and their salaries are doubled. And I've been here 3 years and then nothing has happened." Your boss tells you, "Sorry, I thought you read it in the book. I'm sorry about that. Actually, in this company, the moment you spend 5 years in this company, you are sponsored to go and do PhD for free. And when you return, your salary is automatically doubled." Hallelujah. Now that you hear that, you smile because you know you have how many years left? You know you have how many years left? You smile. You have 2 years. 2 years and yours will come. You will go and you will return and get that. Now here is a question. Suppose 2 years comes, you go, you return, and truly your salary is doubled from 10,000 to 20,000 per month. The question is, what led to the increase in your salary? Was it the education or the experience? Type your answer there. What led to the increase in your salary? Was it the education, the 4 years PhD education that you had, or the 5 years experience that you had? Which one? What led to? What led? Somebody says both. Somebody says education, both. Education, okay? Education, both. Okay? Education, both. Okay? Both. Okay. Somebody says it's both education and experience, covariation. People are speaking econometrics. Some people, oh dear me. Oh dear me. Somebody says neither education nor. Oh, somebody has private chatted me, neither education nor experience. All right, okay. Now let me tell you the reason why you are struggling is because the two variables are multicollinear. Watch the definition I gave you. It is difficult to separate which one is doing that. Okay, you can't tell whether it's education. You can't, because the two variables now are so correlated. You got to have this experience before you can get education. And even if you get education, you need that 5 years experience. You don't say that because I've had a PhD education and I'm here, okay, give me that money. No, you will still need that experience before. The two variables are highly correlated. And you see, that's a problem. Multicollinearity can be a problem in a regression. Because when the two variables are highly correlated, like education and experience are, it becomes difficult to know who is even affecting the dependent variable. And so, one of the assumptions of regression is that there should be no perfect multicollinearity, or there must be no high multicollinearity. Because if there is, we will struggle, like many people are struggling right now. So what do we need? We need the independent variables to be completely independent on each other. Exogeneity must be ensured. The only thing they are doing, influencing, is the dependent variable. They are not influencing themselves in any way. They are not influencing the error term in any way. The error terms themselves are not influencing themselves in any way. By the way, when the error terms are influencing themselves in some way, themselves in some way, this is known as serial correlation. This is it. We spoke about it. Serial correlation. When the error terms are influencing themselves. Okay. When the independent variables are also influencing themselves in any way, it is known as multicollinearity. And then, when the error term and the independent variable are influencing each other cross-carpetingly, that is known as, okay, covariation between independent and regressive. We don't want any of these things to happen in regression. Finally, there must be no specification bias. The regression model that I specified earlier on, some of them had cubes. That's okay if you believe that there's a phenomenon that is exhibited. If you look at some of these things that I've specified, some of them have got cubes. Okay, no problem, provided you can justify theoretically that this thing is multiplying this interactively. Okay, and this is happening that way. There must be no misspecification. Don't go and specify a quadratic model when there's no quadratic relationship. Of course, you wouldn't understand this fully until you've seen clear example. Ladies and gentlemen, you got to understand these principles of linear regression. Is very important to understand the linear regression Gauss Markov assumptions, so that as you go further, because later on you will learn how to break down these assumptions, and you have to